it's a bit small, but I think it would be easier for me if it's vertical than horizontal. Okay, so last time we talked about functions. I'll just remind you a function. For sets A and B, a function f from A to B is a rule that assigns for every A in a unique element. B in B, denoted B is f of A. And now we talked about compositions. So this is what I write here is like the informal or slightly less formal definition of a function. But we saw a completely formal definition in which you define a function as a subset of the Cartesian product of A and B. And we talked about compositions of functions and about the identity function. And today I want to talk about types of functions. So function f from A to B is injective if for any two elements A and A prime in A that are different, f of A is different than f of A prime. The function f from A to B is surjective if for any B in B there exists some A in A such that f of A is equal to B. And finally, a function is called bijective if it is injective and surjective. So maybe just a few synonyms. Injective maps are also called monomorphisms. A surjective map is an epimorphism. and a bijective map is a isomorphism. We will see later on various incarnations of the notion of isomorphism between groups, for example, but the terminology is meant to say in a specific context, like if we talk about sets, there is a notion of isomorphism of sets. We talk about groups, there would be isomorphism of groups, and so on. But you don't have to dwell into this alternative terminology at the moment. And maybe even a third synonym for injective. We say sometimes we say one-to-one. For surjective, we say onto. And is there an analog of bijective? I guess.
So isn't bijective one-to-one?
Bijective is injective, so it is in particular one-to-one, okay. But it's not a bijective. I guess you can say, sometimes people say one-to-one correspondence. Right. And this means bijective. So these are all synonyms, but I will mainly use injective, surjective, and bijective at the moment. So just an intuition, injective map, it means that it does not repeat itself. I mean, if you give me two inputs, then two different inputs, then the output of the function will be different. Surjective map means that for every element in the output set, I can find the source. Okay, I can find some input element that is marked by the function f to this given output. And bijective means both, right? I do not repeat myself. I mean, the function do not repeat itself, and covers the output set B. Right? Surjective, another way to intuitively think about surjective maps is that they cover the output set. And the best illustration of these notions is for finite sets. So let's suppose I have A and B like so. And I could define a function by just drawing some arrows that indicate where does each input of A go in B. And this correspondence would, I mean, this diagram would correspond to an injective function. On the other hand, if I have a correspondence like this, then this would be a surjective map. And finally, if I have a correspondence like this, then this is bijective. So you see that for finite sets, what we should expect is that there would exist as an injective function from A to B if and only if the number of elements in A is smaller or equal than the number of elements in B. And similarly, we should expect that there would exist a surjective map from A to B if and only if the number of elements in A is bigger or equal than the number of elements in B. And finally, there should be a bijective map between A and B if and only if they have the same number of elements. Okay, so this kind of reasoning is sometimes referred to as the pigeonhole principle. And I would like to prove it. So let A and B be finite sets. And then the first claim is that there exists I will write instead of a function, I will write map f from A to B. Let's say an injective map. F from A to B, if and only if the number of elements in A is smaller or equal than the number of elements in B. The second claim is that there exists a surjective map F from A to B if and only if the number of elements in A is bigger or equal than the number of elements in B. And three, there exists a bijective map F from A to B if and only if the number of elements in A is equal to the number of elements of B. Okay, so before we get to the proof, I just want to clarify the statement. Let's say if the number of elements in A is equal to the number of elements in B, it does not mean that every function from A to B is bijective. Okay, only that there exists a function. And similarly to the other two claims, because of course, if you have non-empty sets, you can always define a function that takes all the elements in A into single element in B, for example. This is not surjective and not bijective. Okay, so let's prove it. Okay, suppose if f from A to B is injective, and enumerate A as A equal A1 up to AN. Right? I mean, when I say enumerate, I mean the sets, if you remember, do not come with a particular order of elements. So if I want to work with a particular order, I need to choose one. But that's okay. I chose an arbitrary order, and now for I between 1 and n, denote bi to be f of ai. This is an element in B, right? It must exist. And so the set B1 up to Bn is contained in the set B. Hence, the number of elements in B is bigger or equal than n, which is the number of elements in n. Conversely, if the number of elements in A is smaller or equal than the number of elements in B, enumerate A as A1 up to AN. And B is B1 up to BK. Of course, by the assumption K is bigger or equal than N. And now define f from A to B as f of AI equal BI. Okay? And this is an injective function. Observe that f is injective. Okay, I guess the two other clauses of the proposition are very similar, so I don't feel a particular need to prove them, but if you want, we can do it. Otherwise, you can you can do it as an exercise. Is is this clear? Do you want me to go over the proof of the other clauses?
I can see the relation that the set B is bigger than A from the first part of the proof.
I'm sorry?
I can see the relation that the set B is bigger than A from the proof.
Yeah, well, because in the first part, we have an injective function, and we know, I mean, if the set B contains at least n distinct elements, these must be distinct. These are distinct because F is injective. Right? So if B contains n distinct elements, then the number of elements in B is at least n.
Yes, yeah.
Or
I can find that.
okay, so did you ask about another thing?
But how could it be that? How could it that means the elements of B is bigger than A?
The number of elements.
A number of elements.
You see, here I write
Okay.
included. Inclusion is a relation between two sets. And then smaller or equal is a relation between numbers. So I say number of elements in A is smaller or equal than number of elements in A.
It's about number of elements.
Yes, yes.
Yeah, it's clear.
Okay.
Yeah, that's obvious actually.
Yeah, I guess maybe just for clarity, let me do the second clause. So, and suppose F from A to B is surjective. I enumerate B as B1 up to Bk. And since F is surjective, for every I between 1 and K, there exists an element AI in A such that F of AI is equal to Bi. Right? So so I mean, of course, by the definition of a function, I cannot map one input element into two distinct output elements. So it means that the number of elements in A must be bigger or equal than the number of elements in B. If you want, the set A1 up to AK let's put it like this. A1 up to AK are distinct since f is a function. And this means that the number of elements in A has to be bigger or equal than k, which is the number of elements in B. Conversely, if the number of elements in A is bigger or equal than the number of elements in B, I write, for example, A to be A1 up to AN. And I want to define, so I need to enumerate B as well, B1 up to BK. Where I know that K is smaller or equal than N. Define f from A to B by f of AI equal BI. If I is between 1 and k, right? Because if I is bigger than k, I don't have BI. But that's not a problem. F of AI can repeat into, for example, B1 for I bigger than k. Then F is surjective. Right? It covers all of it. And the third clause, of course, follows from the first and the second. Any questions about the proof?
Yeah, it's a bit like splitting hair, but we defined last week, like this proof relies on indices, right? So we define an index for 1 to n or 1 to k. And last week, if I remember correctly, we were defining the indices as some kind of function because yeah, it was I'm trying to remember, maybe I'm saying something wrong, but I got the feeling that we were doing this, like we were defining an index as an increase every time, like every time we were adding a new item to the index, we were creating a new element that was the previous set and adding a new set, and that felt like a function to me. That's why I'm.
You mean this definition of natural numbers?
Yeah.
Well, this is different. I mean, what I did last time with the definition of natural numbers is kind of a foundational approach, and I mean, I did it to demonstrate how modern mathematics can be constructed from sets. I still didn't define the integers and the rationals and the reals as sets, but later on I will show you how. But this is a kind of orthogonal to what we will do most of the time, because we don't dwell too much in the foundations. I mean, so you can, I mean, just for an illustration of how the foundations are treated, and then natural numbers are just, the usual numbers as you. And if you want, when I enumerate a, you can say that I define a function, let's call it int, from the set of natural numbers 1 up to n,
Right.
into a.
Right.
And then I say that int of I denote as ai.
Right. Yeah, but that's exactly my problem. Because isn't there, like, when you define int, isn't that assumed that it's got to be a bijection?
Yes, this is a bijection. I mean, if a has n elements, then there exists a bijection from the set 1 up to n into a. Yeah, I mean.
Right, but you see, okay, my problem, but okay, we don't have to dwell on this. It's just that it seems to me that to define the bijection, you need the indices, and the indices are defined as a bijection already.
No, this is, I mean, it's a good point. It may look circular, but if you notice, for the bare definition of bijective, injective, and so on, I didn't use any indices. The indices I use only in the proof of the proposition.
Yeah.
So I make a claim. The claim is well defined without indices.
Okay.
And then I prove it with indices.
Okay. Okay. Right. Okay. Doesn't need indices, so theoretically there exists another proof that doesn't use indices.
No, that's not what I'm saying. I mean, you will need to enumerate in the proof, but there is. I mean, you need to distinguish between the statement and the proof.
Right.
I mean, it is circular. If I try to define a notion with the notion itself, this is circular.
Right.
That's a problem.
Right. Yeah.
But if I define the notion without referring to itself, and then I use the defined notion in the proof, then I claim that this notion satisfies a property. Okay. And in the proof of the property of this claim, I use the notion. That's okay. It's legitimate.
Okay.
But to be completely honest, I mean, if you want to prove it from the axioms, you need to do a bit. I mean, to be a bit more formal. But we don't. This is why I call it naive set theory. Yeah. We don't take too much time on the foundations, and I guess you can say intuitively, okay, if A has n elements, then I can enumerate is A1 up to A.
Okay. Yeah.
Okay. Other questions?
There is a question on the chat.
Yes. Okay. YB1. So in the second part of the proof, I said that suppose a number of elements of A is bigger or equal than the number of elements in B. Then what I need to show is that there exists a surjective function from A to B. So I need to define it, right? So I enumerate A and I enumerate B. And by assumption, I know that that K is smaller or equal than N. And now I need to define an actual function that will be surjective. So, I want to cover all the elements in B, so I define f of ai to be bi. This already covers all the elements of B, but it's not yet a function because it is not defined on all input elements of A, right? I mean, I mean, if I is bigger than k, then I don't have bi. If I is equal to k plus 1, for example, then I don't have a bk plus 1, but I might have ak plus 1. So I need to say where does the, I mean, in order to really define a function, I need to say where does, for example, ak plus 1 go. So I don't care where it goes, I just need to define it completely. So I say that it always goes to B1. This is a kind of an arbitrary choice. Yes, I prove by showing that there is one surjective function. Yeah, of course, let's say not every function from A to B would be surjective. Okay. The next is something that maybe is very clear to you, but I think stating it is important because it's going to be a repeated theme. So suppose A, B, and C are sets. And F from A to B, G from B to C, functions. If both F and G are injective, then so is G composed F. G composed F, I remind you, it's a function from A to C. If both F and G are surjective, then so is a G composed F. And the same for bijective. If both F and G are bijective, then so is G composed F. And the reason I'm saying that it is a repeated theme is that properties of functions would almost always, the types of functions that we talk about between sets, but also between groups and between fields and so on. If we have a notion of a type of function, we should always expect that it would be closed under composition. Closed under composition is exactly what is expressed in the proposition. I mean, if you have two composable functions and two of them are of a particular type, then the composition must be of this type. This is an expected property of every notion of a function that we define. So in sets, it is injective, surjective, and bijective. let me show you, let's say, the first part. Suppose F and G are injective, and now I consider this function G composed F from A to C. To show that the G composed F is injective, I need to choose two different elements in A and show that they are mapped into two different elements in C. So let A different than A prime, two elements in A. Then F of A is different than F of A prime since F is injective. Now, since G is injective, G of F of A and G of F of A prime are different, right? You give it two different input, it has to give you two different outputs. But this thing is, by definition, G composed F evaluated at A, and this thing is G composed F evaluated at A prime. This is definition. Okay, so we know that G composed F is injective.
I think there could be a counter case, maybe.
Why?
Because we are for the proposition of that, because we are assuming for the finite set.
No, we do not assume.
Okay. Then.
But of course, if you have a counterexample for finite sets, it's also a counterexample of the proposition, right?
Yeah, I was thinking, I thought we assume finite set.
No, we do not assume finite sets, but this proposition is true also for finite sets. This I mean, I'm claiming a more general.
Yeah, sure then.
So if there was a problem in the finite case, there would be a problem in the proposition, right?
Right.
Okay. So just a general remark. I mean, I try to be very precise. So if the fact that I didn't say that they are finite sets really means, I mean, I would be very careful stating whether my claim is true for only for finite sets or for all sets. So this is the first part of the proof. To show you the second part, for example, if F and G are surjective, and now we consider again G composed F as a function from A to C. And we need to, the claim, I mean, we want to show that this function is surjective. So it means that for every output element in C, there exists an input element in A such that G composed F of A is this output element. So let C be an output element. Since G is surjective, there exists some B in B such that G of B is equal to C. Since F is surjective, there exists some element A in A such that F of A is equal to B. And now I do G composed F evaluated at A. This is by definition, just write it in the second line. This is by definition G of F of A, but F of A is by definition B, and G of B is by definition C. So I took an arbitrary output element C and I found the source A to this Z. So G composed F is surjective. And just like in the previous claim, 3 follows from 1 and 2, right? Because if I compose 2 bijective maps, both of them are injective and surjective. The composition of injective is injective, composition of surjective is surjective. Any questions about this proof? Okay. Maybe one more nice proposition about injective and surjective maps is the following. Let A and B be sets, and F from A to B a surjective function. Then for any set C, and any function any functions G and H from B to C, so I write it with 2 arrows, such that G composed F is equal to H composed F. We have G equal to F, sorry, G equal to H. To maybe to give you like this is a bit abstract. To give you an intuition of what this means, it's kind of we say that F in this case is right cancelable. right cancelable refers to this equation, right? It means that whenever I have an equation like so where f is on the right, then I can cancel f, and I get that g is equal to h, right? But composition is not a commutative operation, right? Even if I could do f compose g and g compose f, it's not necessarily equal. So hence the distinction between right cancelable and left cancelable. And the claim is that a surjective map is the same as, or at least for a surjective map, we have a right cancelability property. Okay. And it's in fact an if and only if, but I don't want to spend too much time on it. Let me just show you how you prove this. So let a B be any element. Right? I want to show that G is equal to H, so I choose an element B in B, and I want to show that G of B is equal to H of B. Okay? Since F is surjective, there exists some A in A such that F of A is equal to B. And therefore, now I do G of B. G of B is the same as G of F of A, which is the same by assumption as H of F of A. But H of F of A is H of B. So I get that G of B must be equal to H of B for any.
Well, I have a bit of an issue with this, because what if, what about all those values that are not touched by F? That's,
But the F is surjective. F touches everything.
oh, F is surjective, not H, G and H. Ah, that's it. That's one. Okay, yeah, thank you.
Okay. Maybe an exercise. We prove the following. That if F from A to B is injective, then it is left cancelable. In that, for every GH from, let's say, A prime into A, if, or such that F composed G is equal to F composed H, we have G is equal to H. Okay, so this is left cancelability. Okay, now would be, I guess, a good time for a break, unless you have any questions. All right, you can think of questions for after the break, and let's start again. So what I want to say about this last proposition and exercise is that it reveals so, some phenomena that is usually referred to as a duality. So once we abstract these properties, I didn't say it, but the proposition is in fact if and only if. So a function is surjective if and only if it is right cancelable, and it is injective if and only if it is left cancelable. And via these reformulations, you can see that injective and surjective are dual notions, right? In the sense that, one of them simply means that you can cancel on the right equation like the one in the purple box, and the other says that you can cancel on the left the equation of the blue box. And so I think it is useful perspective. Generally, as we go on, we will deal a lot with injective and surjective functions with additional properties. And so they are dual to each other, and I think it helps our understanding the context. The next proposition I want to do, well, actually, it's a theory. Let A and B be sets, and F A to be a function. Then F is bijective if and only if there exists a function which I denote as f minus 1 from B to A, such that f composed f minus 1 is the identity function on B, and f minus 1 composed f is the identity function on A. Okay, so in diagrams, what this proposition tells you is that you start with the function f, and f is bijective if and only if there exists a function f minus 1 such that if you go f and then f minus 1, you get the identity function on A. Right here you have the identity. And if you go f minus 1 and then f, you get the identity function of b. And the function f minus 1 is called the inverse of f. Okay, so how do we prove it? Suppose f is bijective. And now I want to define this function f minus 1, which needs to be a function from b to a. So I need to tell you for every input element in b, what is the output of f minus 1 evaluated at b. Since f is surjective, there exists some element, or maybe let's put it like this. For every b in b, there exists some a in a such that f of a is equal to b. And since f is injective, this a is unique. Right? You cannot have any other a prime that is mapped to the input b. We define f minus 1 evaluated at b to be a, this a. And this is well defined. This is a function by the above. Okay, so I define the function, and I want to show the two properties, let's call it 1 and 2. To show this, so let's start with 1. 1 is we want to show that f composed f minus 1 is the identity function on b. Let b be an element in b. Then by definition, there exists a unique element a in a such that f of a is equal to b, and f minus 1 of b is equal to this a. But then when I do f composed f minus 1 evaluated at B, then by definition of composition of functions, this is the same as doing f on f minus 1 of B. But f minus 1 of B is A. So this is f of A. And f of A is B. So I get that f composed f minus 1 evaluated on every element B is just the same element B. So this means that f composed f minus 1 is equal to the identity function of B. 2 is in a very similar manner. So we want to show that f minus 1 composed f is the identity function on A. So I take an arbitrary element A in A, then by definition of f minus 1, f minus 1 evaluated at f of A is equal to A. Right? Because f minus 1, you take an element B in B, you find a source, the source is unique because f is a bijective function, so there exists a source, this is B, right? You take an element B in B, sorry, you take an element B in B and you define f minus 1 on B as, as the source of B under F. So, okay, so if I take the element B to be f of A, then the source, then f minus 1 of B is simply A. And this means, of course, that f minus 1 composed F is the identity function of A. So this is one direction of the theorem, right? The theorem says if you have, f is a bijective function if and only if it has an inverse. So what we proved so far is that if f is bijective, then it has an inverse. Any questions about this part before we move to the next one? Okay, so conversely, suppose f has an inverse, i.e., there exists some f minus 1 from B to A, such that f composed f minus 1 is the identity of B, and f minus 1 composed f is the identity on A. So now we want to show that f is bijective. So how do we show that f is, let's say, injective? I take, so remember, the picture I think is quite helpful for understanding the dynamic of the proof. I am given f and f minus 1, and I know that they are inverse to each other in the sense of these two equations. And now I want to show that f is injective, so I take two elements, a and a prime, in A. And I want to show that f of a is different than f of a prime. So let a and a prime be two different elements in A. Then what I can do is I take f of a and f of a prime, and I apply f minus 1 on them. I guess we can do it like this. And suppose by contradiction or towards contradiction that f of a is equal to f of a prime. Then f minus 1 of f of a would have to be equal to f minus 1 of f of a prime. Right? Because f minus 1 is a function. You give it the same input, it has to give you the same output. But we have this, I mean, f minus 1 of f of a is simply a, and f minus 1 of f of a prime is simply a prime. So I get a contradiction because I assumed that a is different than a prime. And this is a contradiction. So this proves that f is injective. For surjectivity, let B be a typical element, an arbitrary element in the output set B. And I need to find a source for B. What is going to be the source? I'm going to apply f minus 1 on B. Then f of f minus 1 of B is equal to B, because f composed f minus 1 is the identity function of B. So f minus 1 of B, which is an element in A, is a source for B under F. And this means that F is surjective. Okay, so we finished the proof. And as a remark, maybe exercise, show or prove that in the theorem above, f minus 1 is always bijective itself. Okay, so it's really if f is bijective, then the inverse is bijective, and if f has an inverse, then then f is bijective, the inverse is bijective. It's kind of a bijective. You could say that it really means that I can reverse the arrows if I had let's say two finite sets. I could define a bijective function with these arrows, but I could also, I mean, this is, let's say, A and B, and let's say this is F, but I could also define F minus 1 by just reversing the arrows. And okay, so of course, for finite sets, the claim is very easy. It's not. It almost doesn't need any proof. But the main new thing of this theorem that it works for any sets. These sets could be infinite. And maybe slightly less trivial examples. I just need to look it up in the notes. So let A be the unit interval, and B be the interval of all numbers bigger or equal to 3 and smaller or equal to 5. Define f from A to B as the following formula. F of x is 2x plus 3. Define what I want to be the inverse, so I will denote it as f minus 1 from B to A. Let's put it like this: f minus 1 of y is equal to y minus 3 divided by 2. Then I claim, I mean, that f composed f minus 1 is the identity of B, and f minus 1 composed f is the identity of A. How do we see this? Say this is 1 and this is 2. So 1, I take f, I compose it with f minus 1, so I take f of f minus 1 of y. This is f of y minus 3 divided by 2. But what f does to an input is multiply the input by 2 and add 3. So I get y. And on the other side, I take f minus 1 and I evaluate it on an input f of x. This is by definition f minus 1 of 2x plus 3. But what f minus 1 does is subtract 3 from the input and divide it by 2. So this is x. And what this means is that f is the original f, and actually also f minus 1 are bijective. Right? Because we know by the theorem that if we have an inverse, then the function must be bijective. And you can view this geometrically. I mean, I have the unit interval, let's say, and then I have another interval 3 to 5. They are not of the same length, and they do not lie in the same place in the line of numbers. But I can blow up and translate. So I blow up by 2. You can view this function as composition of two things. First, I blow up the interval 0, 1 into the interval 0, 2 by just taking x to 2x. And then I translate the interval 0, 2 into the interval 3, 5 by taking x to x plus 3. Okay, and blowing up is a bijective function, and translation is also a bijective function, and composition of two bijective functions is bijective. Okay, so this this tells you a little bit what happens when I have infinite sets. I mean, they could be of a different size on the real on the line of real numbers, and still be and I would still have a bijective function between them. Okay. However, there is a different notion of size. So you could say that in this example, what may be a bit weird is that the size of the unit interval is small, let's say smaller than the size of the interval 3 to 5. And nevertheless, I was able to find a bijective function between them. And we know in finite sets, I should only be able to find a bijective function if the sets have the same number of elements. So in some sense, this example tells you that the number of elements, if I would define a number of elements for infinite sets, then the number of elements of these two sets should be the same. And it means that size of sets of infinite sets do not correspond precisely to their length on the line of real numbers. However, I could say, so for infinite sets, I could say that the number, the number of elements in some generalized sense of a set A is smaller or equal than the number of elements in B if there is an injective function from A to B. And the number of elements in B is bigger or equal than the number of elements in A if and only if there is a surjective function from B to A. So this is kind of a definition, right? I could extend the notion of size into infinite sets with this with the notions of injective and surjective functions. And I would say that the number of elements in A is the same as the number of elements in B if there is a bijective function between. So now, okay, I can make these definitions, but there is a question if I can find two infinite sets that for which there is no bijective function between them. So, in other words, if I use this notion of size in a generalized sense, would I have two infinite sets that are not of the same size? So let me be more precise. This is an aside. I think we have a bit more time, so I will take the rest of the session to do an aside. And this is Cantor theorem. And what Cantor's theorem tells you is that there is no surjective function from, let's say, the natural numbers to the real numbers. And again, this is an aside. We are not going to use it in the rest of the lectures, but I think it has an interesting application for programming languages. So before I prove it, let me just draw the corollary. Let's see, I think I formulated it. So a fixed programming language and consider the set P bar of all programs in this language. And consider a subcollection P within P bar of all programs that output a decimal representation. a decimal representation, I mean x dot x1, x2, and so on. It's the output of a program is always finite, so it must end at some xn, and to be a valid decimal representation, x needs to be an integer, and all the xi are digits. Um, we can, I mean, we can consider the output of a program P in P, you can say theoretical, let's say. Theoretical output is going to be what happens when I let the program run indefinitely. When we let it run indefinitely. Right, so I get some decimal representation that could go on. Of course, if it doesn't go on, if the program stops to print the decimal representation at some point, then I consider the rest of the decimal representation to be zeros. And now I claim by a Cantor's theorem there exists at least one number x in R for which there is no program P in the language, in fact, but in P as well, whose theoretical output is x. And the reason is that the set of all programs in a given language can be corresponding. We can find a one-to-one correspondence between the set of all programs in a given language and the set of natural numbers. So we can find a bijective map, a bijective function between P bar, this I remind you is all programs, and the natural numbers.
Yeah.
How do I do it? I mean, I have the program with only one character. Let's say it's the first character in the alphabet, then I map it to the natural number 1. Then the program with one character, who is the second character in the alphabet, I map it to 2. and so on. Okay, so if by contradiction, or let's say if for every real number x there would be a program P in P, I mean a program that prints x, we would get a surjective map between, let's say, P and R, right? Because it means for every real number x, you would be able to find a source, P that maps into x. And P, of course, P is contained in P bar. P bar has a bijection to the natural numbers. So I would be able to find at least, this is a bijection, I would be able to find a surjective map from the natural numbers to the set of all programs that actually print decimal representations. And I would take this composition, this would be a surjective map between the natural numbers and the real numbers. And this would contradict Cantor's theorem. So, surjective map N to R, and this contradicts Cantor's theorem.
I missed the part where the surjection is between N and P and not between N and P bar.
I mean, P is included into P bar.
Yeah.
So you can always find a surjection from P bar into P.
From
Right.
P bar into P, yes.
So just compose the surjection. I mean, you can compose these two.
Right.
You have a bijection from N to P bar. It's in particular a surjection, and you have a surjection from P bar to P. The surjection from P bar to P is just saying, for example, you choose an element, just an arbitrary element in P, and you take an arbitrary element in P bar. If it is in P, then you map it into itself.
Right.
And if it is not in P, you map it into the element you chose in P.
Okay.
Okay, so I mean, you like, this is P bar, this is P. It could be infinite. I choose one kind of anchor point, and all the elements P I map to themselves. And if I have other elements, I just map them to here.
Oh, the surjection is between P and P bar, so it's from P into P bar.
No, because
sorry, the other way around.
Yeah, the surjection is from P bar to P.
Into P. Okay, yeah, that's the part I was going to
Okay,
say.
so then I composed it. So from N to P bar is a surjection.
Yeah.
From P bar to P, I can define a surjection. And if any real number could be printed theoretically by a computer program in P, then I would get a surjection from P to R. So composing these surjections, I would get a surjection from the natural numbers into R, and this is a contradiction to Cantor theory.
Does that mean there is a real number that can be represented as a decimal representation?
No, I assume that all real numbers have a decimal representation. But remember that decimal representation could be infinite. So what the Cantor theorem tells you is that in a way you cannot. This is kind of a noble theorem for randomness, if you think of it. I mean, this would be one interpretation, but it tells you that you cannot possibly hope to print all possible decimal representation. There would be one, and in fact many decimal representations that are not printable by any program.
Even theoretically.
Sorry?
Even theoretically, it's not.
Sorry, say again?
So even theoretically, it's not possible to print all the.
Yeah, even in theory, yeah. So it tells you that even if you want to do a kind of a randomness, you have a problem. You cannot just completely randomly choose a real number by a computer program.
Can you come up with an example, or is it just?
This is theoretical, but I thought you would like it.
Yeah.
Let me give you a sketch of the proof of Cantor theorem. Suppose by contradiction that there exists a surjective map f from the natural numbers into the real numbers. This means that I can enumerate. I mean, f of n is some real number. It has a decimal representation. Let's call it xn dot x1n, x2n, sorry, x2n, and so on, right? Now, it means that I can put it in a table. I put f of 1, this is x1 dot x11, x21, x31, and so on. Then I do the same for the second number, f of 2. This is x2 dot x2, sorry, x1 2, x2 2, x3 2, and so on. And generally, I have in the nth number, I have xn dot xn1, xn2, xn3, up to, let's say, xnn, and it continues, right? So now I define a new number by setting y is going to be some y dot y1, y2, and so on. Here, the nth point I have yn, and y, let's say y is going to be x1 x1 maybe we call it, yeah, let's say just for notations, I guess it, well, whatever. We can say that y is going to be x1 plus 1, x1 plus 1. Y1 is going to be x1, so I have basically two cases. In one case, if x1, 2 is smaller than 9, then I do y1 is going to be x1, 2 plus 1. And if x1, 2 is equal to 9, then I define y1 to be x1, 2 minus 1. And I continue in the same fashion. I mean, what I do is that this is called a diagonal argument. I take the diagonal of the table and I modify by plus or minus 1 each element in the diagonal. And by that, I must have defined a new number, because this number cannot be equal to f of 1, because its first element y is different than the first element of f of 1. It cannot be equal to f of 2 because the first digit, the first digit after the dot, y1, is different than the first digit of f of 2, and so on. So by this, I defined a new real number that does not appear in this table. So it means that, and then I get a contradiction, right? It means that this table does not cover the entirety of the real numbers.
And that table can be mapped to the natural numbers. How?
Yeah, this table is in bijection to the natural numbers, because f of 1 is this row, f of 2 is the other row, and so on. Okay, I'm sorry if this was too much, but I thought it would intrigue you a little bit, because it says something about programs. But it would not be, I would not rely on this Cantor part in the next lectures. So you can read more details about it in the notes. And I guess we are over time, but still, is someone interested? Someone wants to ask a question? All right, then see you next week.
Thank you.
Thanks.
Thank you.